like this. Suppose you have following equivalent. One, there exists an Armand combination from B to A, such that KF is the identity on A. Two, there exists A from C B, such that when you do A, C, G, you get the identity of B. And I'll state this equivalently. There exists unit diagram where the inclusion map acts on A, state on 0, and projection on C is this. GHP that ambiance. Yeah. By the way, notice that this is a split exact sequence as well. It was pretty easy to see how to invert these maps. Okay, so here's my strategy. I'm going to show that 1 and 2 are equivalent. I'm going to show 1 plus 2, 2 plus 1, and then I'm going to use them in tandem to get this kinetic diagram. Right. So the first thing is, it's kind of a fun little bit. Let me first make the following note. 1 implies 2. So we have this situation here. Which one do we have? We have K. Let me note if suppose that you have, so this will help us in a moment. Suppose you have X in kernel G, then if you look at X, X and okay, that's going to be my first observation. Why is this? Well, if X is in kernel G, what can we conclude? There has to be some A that goes to it, right? Now just substitute FA for this, and notice the X minus FKX is f of a minus f k f of a. Right? But this is the identity on A, where you f of a minus f of a, which is okay. So that's going to be useful. It's a useful observation for in a moment. So I want to define a map. So now let's get busy and do it. A from okay. How are you supposed to do it? But maybe I don't have an inclusion, right? So I'm starting here and trying to get back here. I mean, how do I sort of get unstuck, right? Because everything's mapping to it. I mean, there are exact sequences out there that are pretty bad, right? Like, for example, if I have this. Multiplication by 2. On that. No way are you getting a function from here back here. The only function from Z2 into Z is the zero function. Right?
So we know that there is a preimage.
Okay, there is a preimage, right?
We need to make it well
defined. Okay, you put your finger on the problem. We know there is some B such that G of B is C, right? So, oh, I'm so tempted. But what's the problem with this? There may be a whole slew of these B's. This is not a well-defined choice.
We choose the one in the kernel.
Yeah, but how do you do that? I like to call this cleaning. Here's what I'm going to do. I choose a B that goes to C, and there may be a whole bunch of them. I'm going to clean this up by I put it in the washing machine, and this is F. Now, KF is the identity, but this is not, and this is probably not the same thing. I'm going to use this to fix this. Okay. Now, this is what I'm going to do. I'm going to take C, and I'm going to pick some preimage, B, and then I'm going to wash it. Right? I'm going to send this here. Now, what I need to do really is to show that this is a well-defined choice. Well, let's see, shall we? Suppose that we have another choice, right? Suppose one is such that suppose I have another choice, right? Now, so right? So I've got basically two things in this relation, right? I need to show that they're the same. Now consider Consider the difference between two choices I made, depending on the choice I made in B1, right? This is B minus B1 minus KF.
This is the J.
What's that mean? Oh, I do that. I always do this. This is why I do algebra, because I don't know how to compose functions. FK. Everybody with me so far? The difference between these two is this. Now, notice now that if we look at G of E minus B1 minus if we look at that, this is G of B minus G of B1 minus G of A E minus B1. GF is the zero map, right? Because of the exactness of that. So this piece is gone. And here I just C minus C, zero. This means by that first lemma I have that this is in the kernel of G. And so, what do we say? That if you have X in the kernel of G, then this is zero. So, B minus B, B1 minus. So, assignment, G of H of C is B minus F can be the world. Everybody okay with that? Okay, so that's really the big hurdle we've had to step over. Because now I'm going to try to convince you that now everything else holds. This is in our model homomorphism. H of C1 plus C2 is equal to C1 is equal to B1 plus B2 minus where B1 plus B2 I'll add parentheses. So this is equal to B1 plus B2 minus FK B1 minus FK B2, which is equal to G of B1 plus G of B2. So this is an orthogonal homomorphism. Well, also, I'll let you verify this. H, this was the easy one, RB, or I'm sorry, RC is RH of C. And the last thing that we really need to kind of convince ourselves is when you do H and when you do G, you get the identity on C. So finally, C, B, and C, if you look at this composition right here, this is equal to G B plus, actually it's minus, wasn't it? Minus FKB, which is G of B, minus GFKB. And again, that's the zero map because you're composing along that exact sequence. So this would be a B, which is C. So, and there you
Right there, and that is H, right?
go. Yes, this H.
No, the
last
last
line.
the last before that.
Right here. Where am I?
The last.
Oh, I see. Yes, yes. There. Okay, let's do the other direction. And now I think this one probably gets the seeds of how you would do the other one. So now we assume that we have now we'll assume that we have the other part of this. So now we have 0. And this time we have the H. So when I do H, then I do Q, you see I do one C. And we have to construct K. So this is 2 implies 1. Okay, so how are we going to do this one? Well, let's define K. K. Huh. How are we gonna do this, you think? So we start with B here. I mean, you know, I don't expect there to be a pullback here, right? Because usually in certain senses this is much bigger than A. So I need to tweak this somehow and get something that I can associate naturally to B back in A. Here is a similar thing here. If you look, at B, there's no real logical way off the top of my head that just a naked B, I can find something that works. In general, when do you expect to take something in B and find something back in A? Yes, when it's in the kernel, and there's no reason to suspect that just some random B I picked is going to be in the kernel. But I can tweak it specifically, get the kernel by doing this. Take B, and again with the washing machine. Now I claim that no, if you look at G, B minus HGB, this is G of B minus GHG up there. But this bit is the identity on C. So this is G of B minus G of B, 0. B is not in the kernel necessarily, but it is. So I am going to choose A of B, take this thing and pick its preimage. And this is a well-defined choice. Can somebody tell me why? F is 1 to 1, so its preimage consists exactly one element, right? So. So, I'll leave this as an exercise. Verify, it's not very difficult to verify this is an Armanto homomorphism. Just write the stuff down and remember the definition of preimage. Now, let's look. And I want to show that this thing works. Okay, so let A be an A and let B be F of A. I want to A, F, A. I hope this turns out to be A is K of B. And how do we define K of B? K of B is equal to A prime, where A prime is a preimage of that special element. HG. Right. So K of B is equal to A prime, where F of A prime is equal to whatever this is. But we know that B is F of A. Minus HG F of A. And notice that FG is the zero homomorphism. So this is F of A. So therefore, F of A prime minus A is equal to 0. Therefore, A is equal to A prime, because this is a one-to-one function. So the upshot is A F of A is equal to K of B, which is A prime, which is A. Therefore, A F is A. Okay. Any questions? Okay, finally, I am going to, so now it's convenient that I have it this way. So now I know that if I have, I'm sorry, if I've got this, then I've got this and vice versa, right? So one splitting gives both. That's really kind of cool. The splitting on one end gives splitting on the other. Now I want to show 1, 2, 5, 3. It's actually 1 or 2, right? Because these are all equivalent, but I'm going to sort of use 1 and 2 interchangeably by name. I want to show the existence of this isomorphic exact sequence. So here's what we have. And it is my burden to build this feed. Build this. And what do we know? We know that these two conditions hold. We know that I've got splitting back here, it's K, splitting back here, H. So with HG is the identity on C, and with FK is the identity. So let's build it.
KV. Yeah.
That's right, if it ain't easy, don't do it. Take an element of B, it's very easy to get an element of A and element of C out of this diagram, right? And that's exactly what I'm gonna do. This would be,
KV.
now, the easy part of this is to verify that it's an orthogonal homomorphism, because both coordinates are orthogonal homomorphisms. And I'll do one of the things, like so. One, two, one, two, equals one, one, plus KV2, right, which is C1, C2, and there you go. And similarly, that's even easier to verify. So what do we have? We have this phi from here to here that's an R-modular homomorphism. I also put in the diagram commutes. Also, if you look at F and then phi of A, let's see what that gives us. This is K F A, and this gives G F A. And KFA is the identity, right? And that's exactly what we need, because the other part of the diagram goes to A comma 0. Right, okay with that? So that we've got it coming there. Also, again, if we have, let's see, phi, and then we do phi, and projection C, what should we get here? This is projection on C of, I guess that's K of B, G of B. Projection on C should be just G of B. So going this way, I get G of B, and going this way, I get G, right? So the last thing we have to do is show it's an isomorphism, right? We've got homomorphism, we've got diagram commute. But somebody get me out of this. Don't make me take the fourth power of that. But type B is an isomorphism. Short 5. Okay, the last little bit to be quite complete is what if you've got this isomorphism, why do you have splitting? Well, let's do 3 and plus 1. We already know 1's close to, yes.
I'm wondering what would be the inverse B of the How would it look like?
Well, I guess what you could do is take the ordered pair AC, right? And what you would do is, I guess you would run these maps in reverse. So if you had AC, try to run this back here, that's essentially C. So I guess it would be something like, you probably want it to be something like F of A plus H of C. So you might check that out. So suppose we have so all we've got is the F and the G, and the fact that this is now, logically speaking, all we have to do is, given this, we just have to construct a splitting here. We could do either one. I just arbitrarily, I wanna try to build this thing right here. And once we've done that, splitting there plus splitting there, I've already done that application, right? So how would we do this? Well, I'm just gonna follow my nose and hope this works out, right? How am I gonna get from B to A? Well, I guess what I'm gonna do is I'm gonna go. This now is an element of A sum C, and what I'm gonna do now is I'm gonna project on A, where, to make clear, now, this is an R module homomorphism. Because phi is pi is, right? That's fairly easy to show. So really all I have to do is show that F and K get the identity. Well, K tells me take whatever's in the argument, so pi A and phi F A, right? Well, what do I know about phi F A? Well, notice my commutativity of the diagram. When I do right, when I do F and then phi, this is this should commute, right? And so, right. So if I have A and A, then this should be pi A right, this should be pi A 0, which is so any questions on that? Yes.
We can prove that K compound with H is 0.
That's right. That's another way to do that. Right. If you prove that, because you can actually directly do this math if you prove that when you do H and then K, it's 0. That's another approach to it. Okay. So last time I told you all also about so I'm gonna step back forward again. So the last thing that I told you all last time was I defined what it meant for a set to be linearly independent, right? And it's exactly what you expect from linear algebra. The set's any linear independent if you have a finite sum, or if you have a finite linear combination of elements of that set over R, and you get 0, then every one of the R's has to be 0. Free modules turn out to be sort of the king of them all in a certain sense, because free modules are important because every module, every unitary module is the homomorphic image of a free module, which is really kind of cool. Every vector space is a free module. Free modules are the modules that best approximate the notions of vector space that you're used to from linear algebra. So without further ado, let me tell you what these are all about. Let R be a ring with identity and F a unitary R module. The following are equivalent. 1, F has a non-empty basis. I will also sometimes consider 0 to be the free module on the empty set. F is the internal direct sum of cyclic R modules, each of which is isomorphic R. Each isomorphic R. Number 3, F is isomorphic to the direct sum of some number of copies of R as an R module. And finally, the fourth one, which is kind of this is kind of one of these universal mapping properties, like we have the direct sum and direct product. 4, there exists a non-empty set X in a function iota from X into F, such that given any unitary R module M and function from X to M, and all my modules are unitary. Any R module M and function, no structure, just a function, F from X to M, there exists a unique R module homomorphism F bar from F to M, such that F bar iota is F. And so let me draw you a picture of this here, as I seem to like to do. So there's a set, there's this function here, such that given any function in the world, you can lift that function to an R module homomorphism at bar such that the dot is impedance. So, what's the big thing that you all probably learned even in the beginning linear algebra course, when you looked at linear transformations from a finite dimensional vector space? Yeah.
His image was completely determined by the image of the element of the base.
That's right. Needed to know exactly what your linear transformation is going to do is you needed to know what it did to the basis elements. And you had complete freedom with the basis elements. You could send them all to zero. You could send them willy-nilly wherever you want. You could stick them to any vector you want. And that's essentially what this last thing is saying. I like to think of this set X as my basis, and this is the inclusion of the basis into the free module. So think of this sort of like a vector space in a way. And this inclusion, that is taking this function here, this takes my basis elements here somewhere over in this module, right? Somewhere over in M. And if this F, if this is true, this takes every basis element to the same place it goes here, and that determines your morphism, right? This is what it means to be a free module. So any R module satisfying one hence all of these is called a free. They are the analog of vector spaces. They're the vector spaces that have a basis, right? You know, I may not have told you what a basis is. Let me be correct. So, reminder, even if it's not a basis of an R module, if it exists, is a linearly independent spanning set. Of course, any R module will have a spanning set. Namely, you could take all the elements of the module themselves, the linear independent and spanning, that's the trick, right? So modules that have a basis, they're free modules, and they are the analog of vector spaces. So if I use this theorem, let me give you a couple of examples. Z is a free Z module. What's the basis of it? Well, one, that works very nicely. By the way, Z is a free Z module as well. What's the basis for that? Five. Now, there's a striking difference between subspaces of vector spaces and submodules of free modules in general. Let me take you back to the old days of linear algebra. Here's a big theorem from linear algebra. Suppose I have a vector space and I have a linearly independent subspace, or I'm sorry, a linearly independent subset. What can I do with that linearly independent subset?
Extend it to a basis.
I can throw some fertilizer on it, sprinkle some water, and grow it to a basis. Everybody agree with that? It's contained in a basis. Notice, 5 is a linearly independent subset of Z, right? Because 5 times n equals 0 means n equals 0. Agree? But 5 is not contained in a basis of Z, right? Because if you add any other element, like 5 and 1, well, all of a sudden that's linearly dependent, because -5 times this plus 1 times this is 0, right? And so this is actually something striking, because, and basically the reason that doesn't work is because it's a field, right? Over Q, there is essentially no difference between 1 and 5, because they're both invertible, right? And so you can always divide by 1/5 if you like. However, in a ring, you don't always, we're not going to get that theorem, that if you have a linearly independent subset of a free module, you can always expand it to a basis, right? How about Q? What's that?
Should, yeah.
One would think, right, because it's got no 0 behind it. Well, certainly Z6. Can somebody tell me what's a big stopper for Z6?
Zero device.
Right, there is no linearly independent subset of Z6 at all. None. Because take any element of Z6, if you multiply it by 6, which is not 0, you get 0. Because everything in Z6 is 4/6. So there's no way, right? I mean, you can't even have one linearly independent element, so you got no chance of having a basis. However, there's certainly linearly independent elements of Q, right? In fact, take any rational number that's not 0. However, you might think about this for a minute. There is no linearly independent set of Q. There's no linearly independent subset of Q that has more than one element. So you might think about that. Okay. I think to prove this, I might do the following. Let me give you a corollary before we prove the main theorem, because I love full corollaries. And this is also, I think, underscores the importance of free modules. Every R module, is the homomorphic image. In fact, if M is finitely generated, then the free module chosen. And if M is finitely generated, the free module can be chosen finitely generated as well. Now, let me leave you with why this is perhaps a non-trivial fact. Z is a free module, and it's the homomorphic image of itself. It's pretty easy to see that Z6 is the homomorphic image of the free module, isn't it? Z goes to Z6 with kernel Z mod 6. Everybody agree with that? The real numbers is a abelian group. Everybody agree with that? There it is. There is some onto homomorphism from the direct sum of some I assure you, very large number of copies of Z onto the real numbers, right? That is not quite as obvious, is it, right? I mean, you have to have uncountably many, and the homomorphism that goes here, of course, this will give you an exact sequence. This thing, this kernel will be extremely complicated, right? But nonetheless, it exists, right? And it's not so clear that R is the rational numbers is the direct is the homomorphic image of some number of copies of Z. And this is the magic of free modules. All of them look like some number of copies of whatever ring you're over, and any R module you can conceive of is a homomorphic image of a quotient of such a module. And we'll explore this more next time. Any questions?